Hey everyone, welcome to this video. Let's talk about reinforcement learning. So, what is reinforcement learning? In reinforcement learning, the model learns through actions within an environment and receiving a positive or negative reward for its actions. In short, the model learns through trial and error. Reinforcement learning is useful for complex environments with unknown rules, many rules, and or rules with high complexity. So, what's a obvious example of this? Well, while you could set up some basic rules for a self driving car, like stop at a red light, what happens if you encounter rare situations, such as how do you emerge in traffic with a broken traffic light during a hurricane with animals and pedestrians running behind you and to your left? It's not going to be easy to program rules for that really rare and crazy situation. But with reinforcement learning, the self driving car can learn how to deal with this rare situation by taking actions and observing its rewards. Another example is we want to teach a robot arm to pick up objects and place it in a bucket. Programming rules for every possible object, shape, size, weight, etc. would be difficult. But with reinforcement learning, the robot arm could learn to pick up objects and place it in a bucket through trial and error, with a negative reward for damaging objects or not being able to place the object in the bucket. Let's go over some terminology very quickly. Agent performs actions. Policy, the agent's brain or decision maker, tells the agent what action to perform in a state. We want a good policy or a good brain for the agent that gives good actions to maximize rewards. The environment is what the agent performs actions on. An action is something an agent can do within the environment. The state is the current state of the environment. And the reward is positive or negative feedback the environment gives to an agent after an agent performs an action, teaches the agent to perform good actions, and discourages the agent from performing bad actions. So, this was a wall of text. How do all these terms come together? Well, check out this diagram. During training, the agent is given the initial state of the environment. The agent's policy or brain uses the initial state to perform an action. So, yes, policy, the brain of the agent tells the agent to perform an action on the environment. Then the environment will have a new state and output a reward. So, yeah, step three, environment has a new state and outputs a reward. Reward is used to update the agent's policy. So, update the agent's brain. So, hopefully, the agent's policy or brain gets better. We want a good policy or brain that gives good actions to maximize rewards. And reinforcement learning does not need weights, which we have been learning about in this AI and deep learning course, although we will soon learn how weights/neural networks can be used in reinforcement learning. So yeah, this will happen soon enough. But for now, we're not using weights/neural networks. Now, let's go into a bit more detail about this reward term. The reward is needed for reinforcement learning because it is what the agent uses to determine good versus bad actions. The reward can be determined by you. For example, you may choose to have a robotic arm successfully placing an object in a bucket as plus 10 points, but dropping and damaging the object as negative 50 points. You decide. The agent wants to maximize rewards over time/cumulatively. So, initial equation that will make sense to most of you is rewards over time equals time step 1 reward plus the time step 2 reward, and so on and so forth. Maybe up to, as an example, time step 100 reward. But that's not, in practice, we don't actually add the rewards like this. But it's a good way to start off to get a basic understanding. Why? Because future rewards can have less value than early rewards. For example, do you want $1 million today or $1 million in a year from now? The most obvious reason you want the $1 million today is because inflation will make the $1 million less valuable a year from now. Regardless of inflation, it would still be better to have access to this $1 million today than a year from now. You would essentially be guaranteed, or another way you can think of this is you would essentially be guaranteed the $1 million today, but a year from now, the person that's supposed to give you the $1 million may have a medical emergency and can now only give you $500,000 a year from now. Or maybe that person goes bankrupt within a year and can now no longer give you the money at all and give you $0. In short, we are less certain about future rewards. We will therefore use a discount rate to discount future rewards. So here's the new equation. Time step 1 reward plus discount rate times the time step 2 reward plus the discount rate squared times the time step 3 reward, and so on and so forth. And the reason we're doing this is because we are less certain about future rewards. We will therefore use a discount rate to discount future rewards. The discount rate will be a number from 0 to 1, such as 0.95. The rewards over time is the discounted sum of every reward given to the agent. Future rewards are discounted more than early rewards. This will make the model focus more on earlier rewards. Let's talk about Q-learning next. Let's learn an easy to understand reinforcement learning algorithm, Q-learning. Q-learning trains a Q function, which can be represented with a Q table. This Q table holds values for a state in action. Don't worry if this does not make sense to you. In a couple of slides, we will show diagrams and pictures of this, and this will make a lot more sense. So imagine we have this world, and there's 4 squares in it, and to win the game, we need to collect the money and not lose the game by falling into this hole right here and getting injured. If we go to the single dollar sign, we get +1 reward. If we go to the $3 signs, we get +3 reward. And if we fall in the hole and make the stick figure get injured or hurt, we get a -100 reward. So let's not fall in the hole. The learning rate will be 0.1, which we will talk about in just a little bit. And the discount rate is what we just talked about in the previous slides in this video. We'll set to 0.95. So Q-learning trains a Q function, which can be represented with a Q table. This Q table holds values for a state in action. So we have the Q table down here. Let's initialize our Q table with all zeros. The state will be the position of the stick figure. So there's 4 positions. There will be 4 different states available. So we have 4 different rows. For each state and action, there will be a cell with a state and action value, which as mentioned will initially be zeros. The episode will end if the stick figure falls into the hole or collects the money. So here's an equation that should be easy to remember and hopefully not too hard to understand. New Q value equals current Q value plus the learning rate times the error. Although if we had to expand the equation out a bit, it's going to look like this. New Q value equals current Q value plus the learning rate times the reward plus the discount rate times the best Q value in new state minus the current Q value. If this looks a little bit intimidating, just remember that all of this is just this simple equation at the very top. And yeah, the error right here will be the best Q value in new state minus the current Q value. And in reinforcement learning, a higher learning rate means you want to remove more of the previous value. Okay, let's start updating our Q table. Here's the equation from before, and now let's fill it out with numbers. So this was previously a 0, so we put a 0 here. The learning rate is 0.1 because I said so right here. And yeah, in this world, we first go to the right. And so the reward is -100. We fell and injured ourselves. So we'll do the reward of -100 plus the discount rate of 0.95 multiplied by best Q value in new state minus current Q value, which is 0 minus 0, which gives us negative 10. The episode will end if the stick figure falls into the hole or collects the $3 signs, so begin a new episode. And now what do you know? This Q table is now essentially saying, hey, when the stick figure is here, don't go to the right, it's negative 10. And yeah, these zeros don't look that great either, but they are way better than negative 10. So what if instead of making the stick figure move to the right, we make it move down? Here's the equation. Here are the numbers. Let's go over them very quickly again. Current Q value, it was previously a 0. Learning rate is 0.1. The $1 sign is plus 1 reward. So here's the plus 1 reward, plus the discount rate, plus the best, or times the best Q value in new state minus current Q value, 0 minus 0. The new Q value is 0.1. Our agent has only explored the environment twice, but the Q table has already improved significantly. Now when our stick figure is in the upper left-hand corner, it knows, okay, going to the right is really, really bad, negative 10. Going left or up, it seems okay. There are zeros. If we go down, we get 0.1, which is better than zeros. So before training, the Q table is all zeros, and then after training, it gets filled up with some useful numbers. So yeah, before training, the Q table is not useful. Important to note, the Q values in the Q table are the expected future rewards for an action in that state. So yeah, this is the environment where going down and to the right gives us the best outcome. Here's the filled out Q table. And quick review, policy, the agent's brain / decision maker, tells the agent what action to perform in a state. We want a good policy that gives good actions to maximize rewards. And we use Q learning to get a good policy, go down and right. And we can see this for ourselves. So when the stick figure is in the upper left-hand corner, the highest value is 0.1, right? It's better than 0 and negative 10. So we go down. Then we end up in the single dollar sign square, which is right here. And what's the highest value? Going to the right, 0.1. So we go to the right and we win the game. We get the most money with the $3 signs. So Q learning. Q learning trains a Q function, which can be represented with a Q table. This Q table holds values for a state and action. And the Q table could be seen as a quick reference guide for the Q function. Let's go over the steps. Step 1. Let's initialize our Q table with all zeros. Take an action. Enter a new state. Measure the reward. Calculate a new Q value. Repeat steps 2 to 4 as needed. So after training, we get an optimal Q function, which gives us an optimal Q table. We want that optimal Q table because it gives us an optimal policy or optimal brain for the agent. And that optimal policy gives optimal actions to maximize rewards. And if you're wondering, what does this all mean? Again, it means, in short, the model learns through trial and error. And as I mentioned in this video, there are no weights involved in reinforcement learning for now, right? No weights, no neural networks. But in the next video, we'll get these two things involved and see how it can make reinforcement learning even more awesome. That's it for this video. Thanks for watching.